Hello everyone and welcome to the Big Bang. Today we will cover timer circuits, or more specifically the 555 timer integrated circuit, or IC. This is basically a circuit that makes decisions based on a set of inputs you can provide for it. You can probably name multiple reasons as to why you would want to be able to time certain events in your instruments. So here I will focus more on the basic foundations of timers and less on its applications. Particularly because these timers are not very extensively used anymore. We have fancier stuff these days. The first feature you will recognize when you see a timer will be its shape and look. It is basically this square with 8 connections or pins. So let's go ahead and number them. Each connection will have very specific function, represented by the short hands listed next to each pin. Do not worry, we will break down their definitions shortly, although I want you to also recognize what a 555 timer would look like in real life, which is basically a little spider with these 8 pins. Now, onto the different pin definitions. At 1, we have the ground, which is where we quite literally ground the integrated circuit. At 2, we have our trigger, which is basically our input that determines when the output will go high. At 3, we have our output, which can either go high or low. The output voltage will be determined by the power supply. At 4, we have the reset pin. It is also known as the active low input, which can bring the output to low from being high. The bar above the reset word is a negation bar, meaning that when you press reset, the output goes low. At 5, we have the control pin. The control pin can change the threshold value as needed. At 6, we have our threshold input, which will determine when your output goes low. At 7, we have the discharge pin, more on that shortly. And at 8, finally, we have our power or VCC pin. The voltage value normally varies between 1.5 volts and 5 volts. One of the plots you'll be playing with is the output over time plot for the 555 timer. You should expect to see a signal that stays at 0 volts, then jumps up to the voltage of VCC and falls back down to 0 after a while. First, note that the output will jump to VCC or high when the trigger goes below a voltage value of VCC divided by 3. Then the output will go low when the threshold goes higher than the control value, which is normally 2 times VCC divided by 3. Alternatively, the output can also go low upon active low reset. You can play with the timing function by connecting resistors, capacitors, or other components between the 555 timer pins. Now, back to the discharge pin. The discharge pin is an interesting one. It will become a switch to ground with 0 ohms when the output is low, but it will be an open circuit when the output is high. In this video, we will cover 2 kinds of 555 timers, the monostable and the astable timers. Let's start with the monostable. The monostable timer is also called a single-shot timer since every time the trigger falls below 1/3 VCC and triggers the output, only one monostable pulse is generated. This monostable timer then generates a single pulse of constant width once the trigger falls below 1/3 VCC. You could say then that the output is logical since it is either high or low. The arrangement of circuit components needed to create the monostable timer is shown in this figure. Notice that you do not need much more than 1 resistor and 2 capacitors, where one of the capacitors is just to keep the voltage constant at the control pin. The period of the pulse once it is activated, or for how long the pulse stays high, is determined by multiplying the resistor resistance by the capacitor capacitance, then by the natural log of 3. This period will be the same every time the pulse is activated. Notice that the capacitance is not the capacitance of the capacitor near the control pin, so be careful to not confuse the two. By changing either your resistance or capacitance, you can modulate the pulse period. That is, you can control for how long the output stays high once it is activated. The plots you would care about for the monostable timers are the trigger voltage over time plot, the capacitor voltage over time plot, and the output over time plot. As you can see, as the trigger goes below 1/3 VCC, the capacitor starts charging and the pulse shoots high. Then, and this is important to take note of, independently of what the trigger voltage is, after that fall below 1/3 VCC, Once the capacitor charges and reaches a voltage at 2/3 VCC, the output will fall back down from VCC to 0. This means that you can keep the trigger at below 1/3 VCC for as long as you wish, since the capacitor charging and reaching 2/3 VCC is all that determines the pulse width of the output, which will be the same every time and depend only on the capacitance and the resistance in your circuit. Although, as you might expect, if you would like for the output to pulse again, you would want to bring that trigger back up. Enough of the monostable timer for now. Let's briefly cover the astable timer. The astable timer can also be called an oscillator since it generates a periodic square wave, and not that single pulse shot produced by the monostable timer. The circuitry of the astable timer looks slightly different because you will be including a second resistor. Since the astable timer produces a square wave, we can now calculate the period of high output and the period of low output, that is T high and T low. T high will be R1 plus R2 times C times the natural log of 2, where C is the capacitance, and T low will be R2 times C, the capacitance, times the natural log of 2. With the astable timer, once the trigger falls below 1/3 VCC, the output goes high, and the capacitor begins to charge. The capacitor continues charging until the capacitor voltage is 2/3 VCC. At that point, the output falls back down to 0, and the capacitor begins to discharge. The capacitor will keep discharging until the capacitance voltage hits 1/3 VCC. When this happens, the output will be triggered again and the next pulse will be generated, restarting the cycle. Sometimes you may either be given or asked for the duty cycle of your 555 astable timer. The duty cycle is simply the fraction of the time the output is high. You can calculate it by dividing the period of the high output by the sum of the period of the high output and the period of the low output. In a problem, you can use the duty cycle to calculate T high and T low, and later decide what values of resistance and capacitance you need to produce that duty cycle. I am including a link to a simulator of the astable 555 timer or the oscillator in the description. And I know this was quite a bit, so I'll let you digest everything now, and I will see you next time.